Hey guys, kind of here. So we're going to do a really kind of fast job of going through electrical circuits, but I want to give you some of the basics that are going to help you do calculations in terms of using Ohm's law and looking at voltage, current, and resistance within a circuit. All right, so let's go ahead and jump right in. The essential questions for today, number one, how are series and parallel circuits similar and different from each other? Number two, how do you calculate voltage, resistance, and current in series versus parallel circuits? Number three, what are the benefits of parallel circuits as opposed to our series circuit? And what is a short circuit? Let's jump right in. Okay, so first of all, we need to make sure we understand what a circuit is. A circuit is simply a closed path that electric current can flow through. Okay, if the current circuit is broken by either removing a battery or the light bulb or one of the wires, current's not going to flow. And this is essentially how a switch works. The switch takes a piece of the wire out and then puts it back in when you turn the switch on. So we can open and close that circuit to allow the electricity to go ahead and flow through it. Now we're going to talk about two types of circuits. We have series circuits, which is just what it sounds like, where all goes in a series. And we have parallel circuits, which are those that have multiple branches where it can go in one branch or the other branch. So in a series circuit, the current has only one loop to flow through, whereas a parallel circuit contains two or more branches for which the current could go ahead and pass through. So let's start by taking a look at series circuits. As we mentioned, it only has one path by which it can go ahead and travel, and the amount of current is going to be the same at all points in a series circuit. Let me say that again. The amount of current is the same at all points in a series circuit. So here is a representation of a series circuit. On the left, you can see a drawing that shows the actual bulbs and the switch, etc. On the right, you see what's a circuit diagram showing the same circuit, actually. You've got your battery, okay? The symbol for the battery is over there on the left. You've got your resistors, which in this case, we're using the resistors to represent the light bulbs. Some places you'll see them use a different symbol to go ahead and represent light bulbs, but we have those as well. And then we have the switch, okay? So if this is the light bulb here, this is the light bulb here. This is the battery here. This is our battery here. This is our switch here. This is our switch here. So all the same pieces are kept in the diagram as we have in the actual drawing of the circuit. Here they are again. Take a minute, make sure that you understand the symbols, and then we'll go ahead and label them. Okay, so let's go ahead and label these just to make sure we know. Let's start out over here with our battery. Okay, so this is our battery. And in the diagram, this is our battery right here. We have our light bulb. We actually have three of them. And we have our light bulb. And this is the symbol for a resistor, which the light bulb is a type of resistor. It slows down the flow of the current, and it goes ahead and uses that to heat up the coils in the light bulb to go ahead and produce light from the glowing portion. And then we have the switch. And here is the switch. Okay, so pretty straightforward. You'll get the hang of this, just needs a little bit of practice. All right. Next thing we want to do is starting to look at resistance, current, and voltage within a single circuit. And we're going to start by taking a look at adding series resistances. Now, each resistance in a series circuit adds up to the total resistance of the circuit. This is important because we're going to show you two different setups, one for series circuits and a different one that's going to go ahead and take a look at parallel circuits. Okay? So if we have a circuit diagram here, we're looking at the total resistance for the entire circuit. It is simply the combination of adding R1, R2, R3, and so on and so forth to produce the total resistance. Okay, remember our unit for resistance is going to be in the form of ohms, and the symbol for ohms is the omega. Okay. So here it is again. In this case, we can take a look that go ahead and R1, R2, and R3. Notice that we just go ahead and plus, 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 add them all together for a total resistance for the series. Now, this only works because All of the current has to flow through all of the resistors. There's no option like we'll see later on in a parallel circuit. So light bulbs, resistors, motors, heaters, they all have much greater resistances than the wires and batteries do. So in a particular example like this, you have a series of 3 bulbs. They're all 1 ohm. So we can very easily go ahead and add them all together to go ahead and get our total resistance. And you see here, we've got a 1.5 volt battery. We've got a 1 ohm, a 1 ohm, and a 1 ohm for a total of 3 ohms of resistance in this particular circuit. So let's go ahead and try calculating it. So how much current flows in a circuit with a 1.5 volt battery and 3 1 ohm resistances, let's say the bulbs in the previous example? Okay, so we are trying to look at current. And if we go ahead and start out, we should know that we have Ohm's law. And Ohm's law tells us that current is I. So current is I. This is voltage, which is V. And this is resistance, which is R. And our equation is V equals IR. So we have the voltage, 1.5 volts, equals the current, which is what we're trying to solve for, and the resistance. But we have 3 1 ohm resistances. So before we can put our R in here, we have to solve for total resistance. So R total, in this particular instance, is going to be equal to R1 plus R2 plus R3. Okay, because they are in series. This doesn't work when we do parallel. So we go ahead and do 1 ohm plus 1 ohm plus 1 ohm gives us a total of 3 ohms for our total. This then we can go ahead and put back in over here, 3 ohms, and then we can go ahead and solve the equation. We divide both sides by 3 ohms, and we end up with a current of 0.5 amps equals I. Okay? And so that's how you go ahead and solve these types of problems. All right, there we have our setup from what we saw before. Okay, and last night I got 0.5 amps as well. Okay, so when you go ahead and take a look at these types of setups, you can see that we have a relationship because of Ohm's law where the current in a series circuit is going to be the same at any point in the circuit because all of the current has to flow through that one pathway that goes from the high potential to the low potential, the cathode and anode that we talked about last time, to go ahead and run if we're using direct current in a battery. Now, voltage in a series circuit. Each separate resistance creates a voltage drop as the current passes through it. Okay, so as current flows along a series circuit, each type of resistor transforms some of the energy into a different form of energy. Ohm's law can be used to calculate the voltage drop across each resistor. All right, so here's our battery. We start talking about 9 volts, 0 volts, adding up all the different voltages. We have 6 1.5 volt cells inside this 9 volt battery. All right, so of that total 3 volts in this particular power setup, we have 2 resistors. One's a 2 ohm resistor and one's a 1 ohm resistor. If we're using 1 amp of current, which is, remember, the same throughout the entire circuit, the total voltage drop has to add up to the total voltage because it's going to end up being 0 by the time we get to the end. So if we have a greater resistance, we're going to see a greater voltage drop in that particular section. Okay, in the second part, we have a lower resistance, and therefore we have a lower voltage drop, but we have to get rid of all of the voltage going from the beginning to the end. All right, now let's take a quick look at parallel circuits. Parallel circuits, as we mentioned, have multiple pathways for the electricity to flow through. And because there are multiple pathways, the current is not going to be the same at all points in the parallel circuit. Some of the current is going to go through one branch, some of the current is going to go through another branch. So once again, here are our diagrams. We want to go ahead and go over this very quickly just to make sure we can identify the pieces. When we go ahead and start here, we have our battery. Over here, we have our battery. Notice that this battery is representing a 3-volt potential difference. We start out with 3 amps of current, but notice in the diagram, once we pass a branching point, the current splits. Most of it's going to go in the path with least resistance, and the rest is going to go through the paths that are going to go ahead and have a certain amount of resistance. So in this case, because we have 3 3-ohm resistors, it's going to be the same. And so each branch is going to end up having 1 amp, 1 amp, and 1 amp go down it. And then when they combine here, if we were to do these, okay, we have 1 amp going there, we have 2 amps going here. We have 1 amp at this point and 1 amp coming down here. This is 1 amp as well. Now, when we come back in, we've got 1 amp, but now we've got this other 1 amp coming in. So now here we have 2 amps. And back here, we're going to end up with 3 amps again. So all of our current is back together because it's split apart to cover the different pathways, but then it combines back together when we get towards the end of the circuit. All right. So the way we can calculate how much is going to do this is because of Kirchhoff's current law. All current flowing into a branch point must equal the current coming out of it. Okay. So you can see the 3, the 2, the 1, each time a branch comes off, you're going to go ahead and lose some of that current to the branch, and some of it's going to continue on into the other branches of the circuit. Now, these pathways, as I keep saying, are typically called branches, and current through a branch is also called the branch current. Okay, so the branch current is what is going through that pathway, not the entire circuit. So when analyzing a parallel circuit, remember that the current always has to go somewhere. The total current in the circuit is the sum of all the currents in all the branches. At every branch point, the current flowing out must equal the current flowing in, and this is known as Kirchhoff's current law. Okay, very simply, you can see it here. 3 amps coming into the branch point, and then we have 2 amps going to the branch point on top, and 1 amp going to the branch point on the bottom. But the total current, the 2 plus the 1, equals the 3 that we started with. Now, voltage and current in parallel circuits. In a parallel circuit, the voltage, this is important, this is different from what we saw in series. In a particular circuit, the voltage is the same across each branch because each branch has a low resistance path back to the battery. The amount of current in each branch in the parallel circuit, however, is not the same as we just saw with Kirchhoff's current rule. The resistance in each branch determines how much current goes to that particular branch. Adding resistance in parallel provides another path for current, and more current flows. When more current flows for the same voltage, the total resistance of the circuit actually decreases. That's counterintuitive. And this happens because every new path in a parallel circuit allows more current to flow for the same voltage. Now, here's where there's a big difference. When we were doing series resistance, you simply could just add them all up, R1 plus R2 plus R3. But because of the fact that more current flows for the same voltage in a parallel circuit, we add them differently. Adding resistances in parallel, 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3, and so on and so forth. So they're not going to be necessarily the same. A circuit contains a 2-ohm resistor and a 4-ohm resistor in parallel. Okay. Calculate the total resistance of the circuit. First of all, you always, like we did with all of our problems before, want to draw out a diagram. Get a mental image of what it is that the problem is telling you you have. In this case, we've got 2 resistors, one that's a 2-ohm resistor, one that's a 4-ohm resistor. We still have to have a battery, And that battery is going to give us a certain amount of drop within the system or potential difference or voltage. And we want to calculate the total resistance using this new formula we just got because they are two parallel pathways. So here's our drawing. Okay. In this case, we want to add them a little bit differently than we did before. So it's not R1 plus R2 plus R3. Instead, we want to go ahead and calculate it with 1 over. So 1 over R total is equal to 1 over R1 plus 1 over R2. There are only two resistors here. So 1 over R total equals 1 over 2 amps plus 1 over 4 amps. Now, in order to add these together, we have to go ahead and get the least common denominator. So we're going to go ahead and use 4 times this by 2. So that's 1 over R total equals 2 over 4 plus 1 over 4. Okay, which equals 3 over 4 omega. Now, notice that R total is on the bottom. Okay, on the bottom. So what we need to do is invert this whole thing. So then R total is equal to 4 ohms divided by 3, or 4/3 ohms. R total is equal to 1.3 repeating ohms. Okay, and what did we get last night? Let's take a look. Hey, look at that. Okay, so this is how you go ahead and calculate it. So you have to identify first and foremost if it's a series or parallel circuit to find the total resistance for a circuit. If it's series, simply add them up. If it's parallel, however, you have to add them as inverses, which is going to do this full fraction setup that you just saw. And then you have to remember to invert it back to get R total so that you don't leave it as 1 over R total. Okay. All right. Let's try another one. Two bulbs with different resistances are connected in parallel to batteries with a total voltage of 3 volts. There's our volts. Calculate the total current supplied by the battery. Okay. So we have a voltage. And then let's go ahead and look at our circuit. Well, in this case, I'm going to go ahead and draw out our circuit. We have a 3-volt battery, and we have a 3 ohm and a 0.5 ohm resistor. Okay. Is this series or is this parallel? Well, hopefully from the context clue up top, you can tell that this is going to be a parallel circuit. Okay. Maybe it's easier to draw it in this form right here that you see on the left. This is what I usually would go ahead and do. Okay. So once we do that, we need to go ahead and find out the resistance, and then we can go ahead and calculate the current. All right. And we're looking at total current, so we just need the total resistance. Now, remember 1 over R total is equal to 1 over 3. Oops, that's not a good ohm. Let's try that again. Plus 1 over 0.5 ohms. All right, so if we're going to get to 3, we'll do 1 over 3. So 1 over R total equals 1 over 3 ohms plus, what is that, 6 over 3 ohms. So that's 1 over R total equals 7 over 3 ohms. Invert that, right? Let's see, and that's going to equal, wait, does it want calculate the total current supply? We can't do it this way. We need to go back and do this for each individual one. So let's go ahead and do this a different way. We still need to go ahead and think about things in terms of the 1 over R total, but we need to find how much is in each pathway, how much current is in each pathway. Okay, so let's go ahead and try this again. we've got one part, which is going to do current, V equals IR. So 3 volts equals I, and resistance 3 ohms. So in this case, we divide both sides by 3 ohms per ohm. So we end up with a current of 1 amp. And this is for this first pathway. Then we do the same thing. We go ahead and run our 3 volts equals I, in this case, 0.5 ohms. It's a horrible ohm. And this one is going to equal 6 amps. So this will be for R2, this will be R1. Then we can go ahead and add them up. 1 over R total equals 1 over 1. Let's see. Oh, we should just add them together. Okay. So that's 7 total amps that would be added up here, right? Since we already have amps. So 1 amp in this path. We have 6 amps in this path plus 6 amps equals a total of 7 amps. Yeah, that seems right. Okay, so we have 1 amp in this pathway, 6 amps in this pathway for a total of 7 amps coming from this original source. And let's see what we got last night. Good, 7 amps. All right. Okay, so hopefully you're getting an idea of how to go ahead and do this. And by me making mistakes, you're getting a chance to kind of see the pitfalls of not thinking it through all the way ahead of time. Now, parallel circuits have a lot of advantages over series circuits. Because you have different branches, there are 2 big advantages that you have. One, each device in the circuit sees the full battery voltage. That's a huge one, so you can have more potential difference for each device that's in the circuit. And 2, each device in the circuit may be turned off without stopping the current flowing to the other parts of the circuit. If there were a series, think about like the Christmas tree lights. If I were to go ahead and take out one of the bulb, the whole strand goes out. But with parallel, that doesn't happen. I can have the bulb go out and everything else keeps working just fine. I just need to go ahead and replace that bulb. Lastly, we have this concept of short circuit. Now, a short circuit is simply a parallel pathway that has very low resistance. So it's not meant to go that way. It doesn't go through any of the resistors that we're trying to power. It's a short circuit. So short circuits can be made accidentally by connecting a wire between 2 other wires that are at different voltages, and it's going to take that path of least resistance. Most of the current is going to go through the short circuit. They can be very dangerous as they can draw huge amounts of current away from the typical circuit. So here's a demonstration. You can see that the normal pathway is going to go ahead and go through a resistor, light bulb, whatever that ends up being, but the short circuit skips it. Okay, it's going to go to the other side of the circuit without actually going through the resistor. That is definitely the path of least resistance. That is where it's going to end up heading to. So all circuits work by manipulating currents and voltages. The process of circuit analysis means figuring out what the currents and voltages in a circuit are, usually using Ohm's law, and also how they are affected by each other. Remember, it has to be a series or a parallel circuit, and they work a little bit differently. The 3 basic laws that are the foundation of circuit analysis are Ohm's law, which we've actually talked a lot about, Kirchhoff's current law, at a branch point, current in has to equal current out, and Kirchhoff's voltage law. The voltage drop around any loop has to be 0. Okay, so that's what you need to go ahead and keep in mind as you go ahead and go through this. So lastly, Kirchhoff's loop law.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 87. It's on Kirchhoff's loop rule, which is a powerful tool to look at circuits. And when combined with Kirchhoff's junction rule, which we'll get to in a few videos, it really makes analysis of complex circuits possible. And so the way it's written is the sum of all the voltages in a loop is equal to 0. And so if we were to write that out, V4, so that'd be the voltage of the battery, minus V1 minus V2 minus V3 is equal to 0. So the sum of all the voltages is equal to 0. Now, how does that work? Well, remember the battery is a voltage lift. It's giving charge potential energy, and then we're losing that energy through this resistor, and that resistor. And so the sum of all of the voltage differences is 0. The lift minus the drop minus the drop minus the drop is equal to 0. Now, conceptually, a better way to think of that is like a roller coaster. When you're on a roller coaster, when you start, there's going to be a lift. So that's going to lift you up to the top of the roller coaster. Now the cars have potential energy, which is converted into kinetic energy. And if they play it right, you're going to get right back to the beginning again with no energy left. And so Kirchhoff's loop rule is really just the conservation of energy in a loop or in a simple circuit. So the voltage or potential difference around that whole loop is going to be equal to 0. So we could look at, for example, a battery and a resistor in a simple loop. The voltage lift plus the voltage drop is going to sum to 0. Now, how do you figure out the voltage of a resistor? Remember, we simply use Ohm's law. And that's all you have to know about Kirchhoff's loop rule in Physics 1. In Physics 2, we're going to add capacitors and then also parallel circuits to it. And so if we think back to that roller coaster, as we store energy in this sphere, it's just like storing energy in the charge across a battery. And when we let it go, we can lose some of that energy. We could gain some back. We could have another battery. We could lose some, gain some, lose some. And so you can have a really complex circuit, and we can solve it using Kirchhoff's loop rule. So think of it more like this. So we've got a battery, which is like the lift in a circuit. It's giving those charge energy or potential difference, and then they're losing that energy. They come back to the battery again and they're gaining charge. This is a pretty simple model. Charge is going to be distributed through this whole thing, but it's a good way to think of what voltage is. And that's why we can't just measure the voltage through something. It has to be across something. For example, across a battery or across a light bulb. And so voltage is equal to the work done by the charge as they move. And so if we were to move, for example, 1 coulomb of charge, we could do 1 joule of work. That's what a volt is. And so let's make that usable. Let's not just short out our battery. If we put a light bulb here, as that charge moves through it, if it's a 1.5 volt battery, we're going to be able to generate 1.5 joules of heat and light coming out of that light bulb. And so if we look at a circuit like this, Kirchhoff's loop rule lots of time is written like this. The summation of the voltages is equal to 0. So the first thing you have to figure out is which way is the current flowing, and then just basically current we'll say is flowing from the positive to the negative. So you can think about going through this loop in a clockwise fashion. To use Kirchhoff's loop rule, you have to start at some point and be able to return to that same point by tracing out the circuit. And so we're going to say the sum of our voltages is equal to 0. So we'd write it out like this. We're going to start with a battery. The battery, since it's a lift, we're going to give that a positive value. So positive V1 minus V2 minus V3, because we're losing that potential difference in each of these resistors here, is equal to 0. And so we could solve for V1. V1 is equal to V2 plus V3. So let's do a simple problem. Let's say we have a 9 volt battery. We have a 10 ohm and a 5 ohm resistor right here. And then we've got a current going in that direction like that. So first thing we have to figure out is, well, what's the current going to be in this circuit? So we've learned earlier that we could just add these two resistances together. So that's going to be a 15 ohm resistance on this series circuit. So we're going to put 15 ohms right here. What's our voltage? That's given as 9 volts. And so we could solve for the current. It's going to be 0.6 amps. So now we just go around and we can use Kirchhoff's loop rule. So if we look at this resistor right here, what's its voltage going to be? Well, we just use Ohm's law again. We know the resistance is 10. We know that the current is 0.6, and so it's going to have a voltage of 6 volts. What's the other one going to be? It's going to be 3 volts. And so you can see that the addition of this 9 volts minus 6 volts minus 3 volts is equal to 0. And so to think about that, and this model really works for me, think of that same circuit drawn like a roller coaster. So we could say the battery is right here. And so how much potential difference do we have, or potential do we have at the beginning? 0 volts, but we're lifting it to 9 volts as we go through the battery. We're giving it potential energy. That charge has potential energy. As it moves through the wire, that 9 volts is not going to change throughout here until we get our next resistor. And so this is a 10 ohm resistor. If it starts at 9 volts, what's it going to be as it gets to the bottom of that? It's going to be 3 volts. So we're going to have a voltage drop of 6 volts. And then that goes to 3 volts and back down to 0 volts on the second resistor that's going to be inside. Now if we do a simulation of that, this is a PHET simulation. I've got that same circuit drawn. So it's going to be 9 volt potential difference across it. We could look at the amps, and that's going to be 0.6 amps. Again, we just added those resistance, and it's going to be the same, current through every part of that circuit. And then the next thing we can do is just verify that those voltages are correct. So if we look across the first one, it's going to be 6 volts across that first resistor. And then if we were to look across the second resistor, using our voltmeter, again, we have to check it across that element. It's going to be 3 volts right here. But what would happen if we now make it a parallel circuit? So if we're going to build a parallel circuit on the other side, and let's just put a 10 ohm resistor over there. So if you think back to that roller coaster analogy again, what's going to happen as we move through that other circuit? Well, we had potential energy right here. We have 9 volts of potential energy here. We're going to have 0 volts of potential energy when we get back to here. And so what's going to be the voltage drop across that? It better be 9 voltage drop, 9 volts of voltage potential difference, and it's going to be a 0.9 amps. And so we could check that using our ammeter and then using our voltmeter. So we get a 9 voltage drop across there. Now, as you move into physics 2, you have to understand what's going on with not only resistors, but capacitors. And capacitors, remember, will store charge along plates. And so now we've got a simple
For what we're doing,
circuit. I've
you
drawn
won't
the
have to
electrons
do.
moving in the circuit, or
For what we're doing, you do not have to do capacitors. We will not be covering that in this class. If it was an AP physics, that might be different, but we're not going to be doing capacitors. You are not needed. You don't need to know that part.
in this time. And so we've got a 0.9 amps. So we've got movement right there. If we were to move.
Okay. If you want to watch the rest of this, you can go ahead and link out to it. This is from Bozeman Science. He's a great guy. He's got good concepts and good explanations for a lot of his concepts. So this one's on Kirchhoff's loop rule. Those are the main things I need you to go ahead and know. All right. Well, that's what I've got for you today, guys. Take care of yourselves. Stay healthy, stay safe, and I'll talk to you soon. So long.